Hey, well, welcome everybody. Thank you for attending. We're going to be talking about some recent RISC-V additions into Zephyr. So let's go ahead and get started. So just some brief introductions. This talk is going to be kind of a co-presentation between myself and Alexander Mernia. Alex is in the chat, so if you have questions, you can, as Maureen said, you can ask, or you can type in the chat, and Alex will be able to respond to those. We both work for Bayliba. We are an embedded software shop, primarily based in Nice, in the south of France. We work a lot with open source software, so we're very active in the Linux community. We're also pretty active in the Zephyr community. We have a few of our team that are maintainers and collaborators in the Zephyr project. But we're also working on U-Boot and trusted firmware and Opti and Yocto and all sorts of testing stuff. And so Alex is the primary engineer that worked on this work. I will be doing the presentation, but Alex is the one who should get all the credit for the actual code and contributions. Alex is based in Nice. I am based in Seattle. So it is 7 a.m. for me, so I'm still waking up a little bit. So if I'm a little bit slow in reactions, that's what's going on. And I have contributed to Zephyr, but my very complicated patch to Zephyr consists of a grammar fix in the documentation. So Alex is the one who actually did the real heavy lifting here on the code. So I'll be doing the presentation and summarizing the work, but he's the one that did the good stuff. A little bit more about our work in Zephyr. So early on in the Zephyr project, I think it was pretty much right when it was launched with the Linux Foundation, we contributed an STM32 port. This work is the sort of RISC-V 32-bit work that we contributed that we'll be summarizing today. We also contributed the 64-bit port for RISC-V, and there's a link to a blog article here that covers that work. And we also got the ARM64 64-bit works merged into Zephyr. So that's kind of just a bit of a summary of what we've been doing in Zephyr. So enough of the bragging about Baylib. Let's get into what this talk is about. So here's just a quick agenda, what we're going to cover. So I'm going to give just to review some of the Zephyr features that that we had to modify or we implemented for this project. A quick intro to some of the RISC-V hardware features that were used to do that, and then we'll get into kind of the user mode threads implementation that we did, and then a quick discussion on kind of the challenges that we came into and what's still left to be done. So let's get into just the Zephyr overview stuff. So presumably this is going to be review for most of you. So I will go over this relatively quickly. But Zephyr has the concept of two different privilege modes, the kernel mode and user mode. So the kernel mode is where the OS itself runs and also where kernel threads run. And this maps onto, privilege levels of the various hardware that are supported. And that's and Zephyr can handle just that. If the hardware doesn't support it, Zephyr can run everything in kernel mode. And it works just fine like that. And in fact, that's how the RISC-V port was working before we contributed this work. So all threads were running at privilege level. But there's also user mode. If the hardware supports another privilege levels or unprivileged levels, you can have user mode, and that's where you can run user mode threads that are protected. They can be protected from the kernel so that they can't damage the kernel. They can't modify any kernel code, but they can also be protected from each other. And in order for that to happen, you need some hardware features that can actually have some memory protection. So that's what we'll be talking about, the RISC-V hardware features that we used. And by the way, throughout the talk, when I have these links with the little Zephyr kite, these are just links to the Zephyr documentation on the topic. There's quite a few places where I just refer to the Zephyr documentation, which is quite good on some of these topics. So. That's what the little kites throughout will just be indications of links to the existing Zephyr documentation. Okay, so also getting into Zephyr for stacks. So one of the things we're doing for this project is to try to separate stacks. So each user mode thread has its own stack, and those stacks include the thread local storage. And combined with an MPU, that allows us to actually separate those stacks and protect them from each other, so the threads can't actually step on each other's stacks. And again, this is kind of, I'm trying to use the same terminology that's used in the Zephyr documentation, which is why the links are here. So the hardware stack protection is what we're going to be talking about primarily later on when we get the MPU involved with the stacks as well. But also there is a software alternative to the hardware stack. So the Zephyr docs talk about stack canaries, and that is something that if your compiler supports it, you can actually have compiler help to insert some canaries into the stack frames that can be checked for stack overflow as well. We're not going to talk about that. There's just a link there to the Zephyr docs for that, but we'll talk about the hardware support later on. Okay, and another Zephyr concept is memory domains. So again, with the MPU-backed user space, by default, the threads are only going to have access to the minimum of what they need. So by default, that's the program text, which is the executable part of the thread, then the read-only data section, and then the thread stack. And the thread stack includes the TLS. So that's kind of the minimum set of data that a thread needs to run. But there are cases where you might want to have threads share memory with each other, or maybe share memory with the kernel, and so on. And so Zephyr provides a memory domain API for that. And so that can be, you can configure those memory domains at static or at build boot time, or dynamically at runtime. So one thing we'll get into later on in the case with RISC-V, you have to be kind of careful with these, because if you have an MPU which only has a few slots to actually configure the various regions, you have a limited number of memory domain partitions that you can actually enable and configure. So you can define these at build time, but they might not actually be available if the hardware doesn't support enough slots. So we're going to get into some of that complexity later that came with the RISC-V implementation. And again, links to the Zephyr docs for the more details on all these features. And then just a handful of the Kconfig options that you may have seen in Zephyr that are kind of relevant to the things we're talking about today. Okay, so let's get into a little bit of the RISC-V hardware features and how they map onto the Zephyr features that we're talking about. So RISC-V spec defines a set of hardware privilege modes. The first one is what's called machine mode, or M mode, in the RISC-V spec. And M mode is the only one that's actually required. So any RISC-V design has to support M mode. All the other ones are optional. So M mode is actually where the Zephyr kernel and threads actually run, and that's where, like I said before we started this work, that's the only mode that was supported. So the kernel and all the threads were running there in full privilege mode. The RISC-V spec also defines an S mode for supervisor mode. That's optional mode. That's actually not present in a lot of the embedded designs, and the cores that we're working on for this project do not have an S mode. But the 64-bit cores that are more common for the Linux port of RISC-V actually support S mode. And then there's user mode, which is also optional in the spec, but user mode is present on these embedded cores like the Sci5E family. And that's the mode that we're using in this work to run the Zephyr user mode threads. And then, of course, you need a way to switch between those various modes, and the RISC-V instruction is called ecall that we'll refer to throughout, and that's basically the trap that allows you to trap from user mode into kernel mode or machine mode. And just an interesting note for those of you who might be familiar with Linux as well, the Linux port for RISC-V actually runs, Linux runs in S mode typically, and in M mode is actually kind of in RISC-V what's called SBI, and it's kind of like the low-level firmware supervisor, kind of hypervisor level things that can run in M mode. So one difference between Zephyr and Linux is that Zephyr is running in M mode, where Linux would run in S mode on the bigger RISC-V cores. Okay. So now on to the RISC-V hardware that actually helps us with the memory protection. So the MPU, the memory protection unit in RISC-V is called PMP, which stands for Physical Memory Protection. And it's important to note that this is actually an optional part of the RISC-V spec. So there are RISC-V designs, obviously, that will not have these. The cores, the RISC-V cores that we're talking about for this project do have them. So like the E family cores from Sci-Fi, for example, which are common cores or common cores that other people design off of, will have that. But PMP is really the meat of the memory protection unit in RISC-V. So the PMP is basically the part that will check all the memory accesses from the supervisor and user modes, and catch them and trap them so that the machine mode code can actually detect when things are being will detect memory faults, basically for modes, for code that does not have the right privileges. And you can actually configure the PMP to check accesses even from machine mode as well. We won't talk about that as much because that gets a little bit complicated, but there's this modify privilege bit is a mode where even from machine mode, you can essentially pretend that you're still in user mode, and so machine mode accesses to user mode memory can still go through the PMP, and you can actually trap machine mode accesses to unprivileged code as well. So that can be useful, for example, in the fault handlers in the kernel. If you want to check if you actually have access or not. So the important thing that I'm going to hit probably over and over through this talk is about the PMP entries. So the RISC-V spec defines 16 entries, basically 16 regions that you can define in the PMP. So that's not a lot of memory regions, but even the spec defines 16. The common cores available more often actually only have 8 slots. So the cores that we're talking about here for this project, we only had 8 PMP entries. So that's basically 8 memory zones or memory regions that you can actually protect at any given time. So that provided a bit of entertainment and complexity in this implementation. So we'll get into some of that as well. Oh yeah, and at the bottom I have a link to the RISC-V specs as well. The PMP is actually part of it's not part of the main spec, it's part of the privileged architecture spec. Okay, so each PMP entry, and remember an entry is just the way that a given memory region is defined. So each PMP entry consists of an 8-bit config register and then an 32-bit address register, or 64-bit if you're on the 64-bit RISC-V. So the config register is basically where the permissions are, and there's a little bit kind of a few more bits to define the type of access. And then the address register. So in the general case, if you want to just define an arbitrary memory region, you actually have to use two PMP slots for that. So you have to use one for the start address and another one for the end address. So there is a special case if the memory region that you want to define is actually a naturally aligned power of 2, which is called NAPOT in the RISC-V spec. Then you can get by with only one entry. So you can see already here with only 8 entries and several regions to protect, it's in our interest to use the power of 2 alignment wherever possible so that we can save on PMP entries. And we'll get into that a bit more because that comes into play quite a bit throughout here. Okay, so that's enough of the overview of the Zephyr features and kind of RISC-V hardware basics. Let's kind of get into what we actually had to implement to make this work on the Zephyr port. Okay, so the first thing we had to do, oops, back a slide. The first thing we had to do is actually add the feature to detect what mode we're in. So there's this API function for user context, and that's what we had to implement. So there's several parts to the code where you actually need to know if you're in user context or not. And so this is the function we had to implement. And unfortunately, in RISC-V, there's actually not a way to check this privilege level check the status of this from all the privilege levels. So from user mode, for example, there's no way to check to validate what context you're in. So we had to explore a couple options. The first thing we explored was to use a system call for that, and which was an option, but the function is actually used quite a bit throughout. So the additional overhead of a context switch was not great. So what we ended up on was basically creating a global variable that's updated whenever we change privilege modes, and then we protect that variable with the PMP so that from user mode it can't be modified, but then whenever we switch privilege levels, the kernel mode code will update that flag. So the advantage of that is that it's very fast, so there's no overhead to check that flag, just check a variable from user space. But the disadvantage is that it uses one of our PMP entries to do that. And as I mentioned, we only have 8, so we're chewing up one already just to protect the global variable. In this case, though, the overhead savings is quite significant, so it's worth it. Whoops. I'm getting Teams notifications on top of my screen. Okay. Okay, back to it here. Okay, so the next thing is actually the system call. So how are we getting, how are we switching modes? How can user space actually access kernel functionality? So before we added user space, there was already a system call handler, because even in the Zephyr port, which only supports kernel mode, we're still using this feature, this kind of system call type feature and the eCall handler. And that was used for the IRQ offload feature and to basically handle thread switching, kernel thread switching, context switching. So this is kind of what the syscall handler and the eCall trap handler looked like before we started this work, and then so now this is all the stuff that we had to add for user space, and this is quite an oversimplification, but to kind of get the idea of all the stuff that we had to add to get the syscalls working from user space. So from user mode, the Zephyr build will build up all the syscall wrapper functions for all the different syscalls, and which then under the hood call these arch syscall wrappers for the different types of different numbers of arguments. And those wrappers actually use this ecall instruction, and the ecall is the thing that instruction is actually the thing that triggers the trap into kernel mode. So from user space, this is how we trap into the kernel mode, and then inside the trap handler is where all the fun happens. So there's the context save as expected, and this is where this is user the is user flag here is the global variable that I was talking about that we protect. So once we trap into the kernel mode, we set the is user flag to false. So now any checks for the using that arch is user context are going to return false. And then we have to check in the trap handler because of the as I mentioned on the previous slide, the ecall handler actually already handles several kernel mode functionality like RISC offload and context switch. So here in this trap handler, we still have all of that code. So we're checking if the ecall came from kernel mode or not. If it did come from kernel mode, we have to deal with the previous stuff, so the IRQ offload and the context switching and so on. But we also need to check if this was one of the system calls to actually switch to user mode, like this arch user mode enter function, or there's another case which is the syscall return, which we'll get to in a second. So we still want to handle any kernel mode traps from ecalls. But then the stuff that we added was to handle the case where the ecall actually came from user mode. So then is all the kind of normal syscall handling. So we have to, load the syscall args that came from the stack frame. We have to make sure that this was a valid syscall, and then of course we call the syscall the syscall itself and do the real work. Now, what gets interesting here is that in RISC-V, the syscall return actually does another ecall. So now this is a case where it's going to essentially be a nested trap handler. So we're going to enter this trap handler again, this time from kernel mode, and then we'll fall into this case where we're checking from it's a kernel mode call, and then it will handle the syscall return. It will clear that user flag, our magic global variable. It will clear that before then handling the return back to user space. So this is all kind of greatly simplified summary of how things work, but it's just to kind of show that how the main points of how we had to change things from the previous kind of kernel only ecall handler to when user space was added, and then the various nesting and stuff that can happen. And of course, in this code is where all the rescheduling can happen and the thread switching happens and all this stuff. But I didn't go into that because that is already in the previous work. Okay. So now, what are we doing with the PMP to actually protect these user threads now that we can switch from user threads, and now that we can have both user threads and kernel threads? So, as I mentioned before, we have a few regions that we want to protect for user threads. So we have the executable text section and the read-only data section. And what the RISC-V port does is actually combine those into adjacent kind of contiguous region. The linker script for the RISC-V port puts those together so they can be defined with a single region. And the permissions for that region are then given to be read and execute. So that's one way to kind of save a PMP entry, is to put those two sections together. The next section will be the thread stack. So the thread stack includes the TLS, also includes the data and BSS sections. So those are the first two regions that we have to protect for each thread. And remember, these are per thread, so each thread is going to have a different copy or their own versions of each of these. So for each of those regions, we also need two PMP entries. So remember, unless they're power of 2 aligned, we need two entries to define each of those regions. So the text and read-only data and then the thread stack will each need two PMP entries. And then this global variable will need one more entry. So we're already up to 5 PMP entries to define these regions just to protect user mode threads. So remember, we only have 8 on these E31 and E34 class cores, so we've already consumed quite a chunk of our PMP entries. So we can reduce that to 3, however, if the text and read-only data and the thread stack can be naturally aligned powers of 2. So that's if that's at all possible. That these are build time choices in the RISC-V port. So you can see the motivation behind using power of 2 alignment, if at all possible. It might waste a little bit of memory, but it allows you to have more regions here. And similarly for the memory domain partition. So let me go back a slide. So this is the minimum memory regions that need to be protected for user threads. But like we mentioned before, with memory domains, there are other ways to share memory between threads and with the kernel mode, and that's these memory domains. So in order to find each memory domain partition, we also use PMP to protect those regions as well. So they can be accessible from user mode, but the user threads cannot, stomp on each other's memory partitions. So there's a few memory domain APIs here that I get into. The first one is the one that just returns how many entries available. So when you're requesting memory domains, this is the function that will tell you if there's any left. So the way that works on RISC-V is it actually looks at the maximum number of PMP entries. In our case, it was 8, minus the number that were used for user space, and so that's already up to 5, like I said in the previous slide. So then there's this, if you want to add a partition, there's the partition add function, and that will look at the size of the region requested, and if it's an arbitrary size, it will just use 2 PMP entries for that. But it does check, this function will check if the range being requested is a naturally aligned power of 2, and if it is, it will only use 1 PMP entries. But again, if you're a little bit careless and you're not paying attention to the alignment, you will use 2 PMP entries for each partition. So if you haven't done the power of 2 alignment, so there'll be 5 entries for your user threads, and then 2 for the first memory partition, and then there's only 1 left, so that's not enough for another memory partition. So already there's no more room with just a single memory partition. So again, this ends up to be a pretty important limitation on the RISC-V, the design of the RISC-V core itself to have only 8 PMP entries. So for those of you out there that are exploring RISC-V designs, I would encourage you to use the 16 from the spec and not limit it to 8, because they get used up quite quickly. And then just one more API function from the memory domain, which is this arch buffer validate function. So this is a function that can be used to check if a thread actually has access to a memory region or not. And what the implementation for that for RISC-V, we actually just walk the PMP entries and check that way. So it validates it directly against the hardware PMP tables. Okay. So as I've been saying throughout, for PMP, the recommendations are to basically use power of 2 alignment where possible. And in fact, the actual Kconfig for the RISC-V design will select the power of 2 alignment whenever user space is defined. So that can be overridden, but that's one thing that the port actually does. But that doesn't affect the memory domains. So the memory domains are more dynamic. So it's actually you need to take care when requesting memory domains that those are aligned if you want to limit the number of PMP entries. Okay, so we've talked about protecting the user thread memory regions, the thread itself, the thread stack. We talked about memory domains, and then another thing that we can protect with hardware is the stack itself. So this Zephyr feature, this hardware stack protection feature, provides an option for the hardware platforms to basically add stack overflow protection in hardware if needed. And so the way that the RISC-V port does that is also with PMP. So we can basically add the way it's implemented now is we add stack guards at the top of the stack, the kernel stacks, the IRQ stacks, and the user stacks with PMP. So there's yet another PMP entry that's needed for those stack guards. So however, this particular feature doesn't get in the way of the user space because these stack guards are put in place only in kernel mode. So when you swap to kernel mode, you can actually replace the PMP entries temporarily until you go back to user mode. So they don't conflict directly with all the ones that I talked about before. So that's why when the kernel mode switch happens, the PMP tables can get updated with the kernel stack guards, and then when user space they switches back to the user space protections. One of the complexities in actually implementing this is the Zephyr config space can get complicated quickly because you can enable and disable user space, you can enable and disable the power of 2 alignment features, you can enable and disable hardware stack protection. So the code has to deal with the cases where any of these can be enabled or disabled. So it leads to the combinations of these features makes the code a little bit complicated, in some cases confusing of why things are done that way. So in terms of readability, it actually is a little bit problematic, but that's part of the reason to deal with this complexity. It's one of the benefits of Zephyr that all these things can be enabled or disabled independently, but it does lead to a little bit of complication in the code. And in the case for RISC-V, it leads to complexities in how many PMP entries are needed, as you can quickly run out. Okay, so that's the bulk of the work that we did. And so I've already hinted at a couple things that were a little bit challenging that we ran into, but here's a few more areas that could use some potential work. So this port was primarily focused on the 32-bit RISC-V design, and based on the Sci5 E-cores. So most of this is the same between 32-bit and 64-bit RISC-V. But there is some of the code that probably needs some validation. The PMP entries are slightly different on RISC-V on 64-bit versus 32-bit, for example. The particular configuration registers there are slightly different, but it's basically the same. But we haven't yet done the validation work on that, and so that's an area that needs some work. And then, like I mentioned, most of the 64-bit RISC-V cores actually have an S mode, which Zephyr doesn't currently support. It only supports machine mode and user mode. And the Zephyr port for the 64-bit might might be interested in using S mode as well, in which case it could use the SBI, the Open SBI work in machine mode, kind of like the Linux port does, and you could actually get some low-level functionalities from standard RISC-V code that way. So that's a potential area of exploration in the Zephyr port for RISC-V 64-bit. The next thing is this is user flag. So this was the global variable that we used to define the context. Right now, that's global for all CPUs. That should probably be done on a per CPU basis. So that's and that there's that variable is 4 bytes already, because that's the smallest region that PMP can protect. So there's plenty of room in that variable to have bits for each core. One of the more interesting things that we came across in the RISC-V privilege spec is this machine trap delegation registers. So right now, as I mentioned in that syscall slide, we have this mix of kernel mode exceptions and user mode exceptions in the same code. So RISC-V actually has these delegation registers where you can separate user mode trap handling and kernel mode trap handling and interrupt handling. So this is something that we thought about exploring, because that could clean up some of the multiple cases that have to be handled in those trap handlers to deal with kernel and user. Could maybe be cleaner and maybe faster if we took advantage of these trap delegation registers. So that's something we're aware of in the RISC-V design, but we didn't actually explore in great detail. And then another area that was kind of a pain is for all of this PMP work that we needed to do, we tried using QEMU for that, and the PMP emulation actually in QEMU is not quite working well. So Alexander actually has a few patches for QEMU that get this a little bit better, but it's still not quite the same functionality as in hardware. So to do the real PMP validation, we ended up mostly relying on the hardware and not on QEMU. So that's an area where there's been some work already by Alex, but I think that's an area that needs to keep going. Okay. So in summary, what we started with was a quite functional RISC-V port, but it was only supporting kernel mode, so everything was running at full privilege level. And now what we have in the RISC-V, the 32-bit RISC-V port for Zephyr, we have full support for user mode threads, for memory domains, for memory protection, and for hardware stack protection. So yeah, so that's what we added. And thank you very much. Open for questions, either verbally or in the chat. See if I can stop my screen share here.
If anybody has a question, feel free to come off mute and ask the question out loud. You don't have to type it in the chat.
Yeah, so one of the questions is any insight about the number of PMP registers. I don't have it. I don't know if you do, Alex. I don't have any, but it seems it's hard to tell the various RISC-V cores that I've looked at. Most of them don't actually list in their specs the number of PMP slots. So in some cases you find this by accident as you get into the hardware. But I know the Sci-5 cores actually have 8 slots.
Okay, so it's architecturally flexible then?
Yes, that's right. Yeah. So
good headphones.
Yeah, the RISC-V spec talks about 16, but it talks about it in a kind of a vague way, and I think we found out only later on that there was only 8 on these E cores. So.
Okay, and is the Zephyr port at least cognizant of the fact that this can be larger?
Yes, it's basically a pound to find, the maximum number of slots in the hardware. Yeah.
Cool. Yeah, that does seem to be maybe a hardship. I asked because I'm actually looking at the Extensa MPU implementation. This is Andy Ross. Hi. I'm looking at the Extensa MPU implementation, which actually has a very similar kind of architecture where it's a comparator-based thing, although it's 4K aligned. It doesn't have 4 bytes. And where you essentially burn the next register to store the end boundary of the region that you're defining in the first register. But their options for hardware integrators are 16 and 32, and you kind of add the transistors up. It doesn't seem like it should be that large, especially when you're comparing it to devices that have like L1 caches and stuff typically. So yeah. Anyway, I was a little bit struck, but maybe it's just these particular devices that are an issue.
Yeah, my only thought was the idea would be for these more embedded cores, they just thought there wasn't very many regions to protect, so let's limit it. And if you really want memory protection, you're going to put an MMU on, and so that's the only thing I could think of. But I don't really have any other insight than that. But yeah, like you said, for the number of transistors to go from 8 to 16, it seems like a no-brainer to me. But. Any other questions?
I guess just for my edification. So you're looking at these are the Sci-Fi V cores. Are those the only ones with the MPUs that are in the market right now, or I just don't know what the hardware world looks like in RISC-V?
Yeah, the RISC-V hardware world right now is kind of all over the place. There are lots of designs out there, but I mean, and I think there are a lot more that are not public as well. So we primarily use those. So I don't have a ton of insight into what else is out there right now.
On this project, I work as well with an FPGA with customer picture on this. Which was an E3031 or E34 core with 60 PMP slots. There are other hardware, but like Kevin says, they are not public.
And just out of curiosity, and this may be more hardware vendor relationship stuff that you wouldn't be privileged to, but I mean, is there a test suite or compliance mechanism? I mean, one of the worries I think a lot of people have about RISC-V is that the specs are out there and then the stuff arrives from vendors and it's not quite right. And you were mentioning the QMU, for example, the emulation not being quite correct. I'm just wondering, do you expect that the work that you've done here is going to just port in a very straightforward way to other cores, or is there some worry about about how it's going to work out?
No, it should work.
Okay, cool.
Yeah, there are some things in the spec. I mean, I worked a lot on 32-bit ARM cores back in the day, and there was I think there are similar concerns to those days where the vendors may or may not follow the recommendations. We did notice some things like there's a bit, for example, in RISC-V that's supposed to indicate whether a trap came from an interrupt or from an exception. And that's defined in the spec. We did find that there are cores that don't actually follow that. QMU doesn't follow it, which was kind of expected. That can be fixed, but there are actually some hardware designs that don't actually do that as well. So there are already signs that there are some things like that that are loosely followed in the spec, and so I think that's probably to be expected. But the port already deals with those things because it's been tested on a few different cores already. But there probably will be some things like that. It's hard to say. Right now, the Zephyr port for RISC-V is relatively simple. I mean, at least compared to something like Linux, right? But but it's been done on a few cores and on QEMU, so we've covered some of those known cases already. But I mean, to your original question about a compliance, I'm not aware if there's some sort of compliance suite that maybe RISC-V Foundation is working on something there. I don't know enough, or maybe there already is something that can test if a core is fully compliant to the spec or not. I'd be interested to know that as well.
Yeah, it just seems like this is a situation where ARM, just by dint of having sold so many CPUs as the kind of a business model, they've got this under control and everything.
Yeah.
With the recent architectures, really just it just kind of works. The
Yeah.
x86 world is not quite so great, but at least the documentation's really good. Even the hardware is comparable, and then you've got things like Extensa, which is where I'm working mostly these days, where nothing is compatible with each other because that's actually their business model, where they configure it for you at instantiation time. And so it seemed like an opportunity to RISC-V to kind of teach the rest of the industry how this should be done, I guess, is kind of what I'm hoping to see. Because it seemed like it was a good, clean architecture, at least as I understood the PMP stuff. So it's not something that is unamenable to sort of like test suites and licensing requirements.
Yeah, and I think the hope would be that getting this work into Zephyr in open source, RTOS, that would help people standardize on the core designs, right, as well. So I hope there's the software will have some influence on the hardware decisions as cores come out as well. Probably wishful thinking, but it's worth a shot.
Well, this looks great.
Okay, well, if there aren't any other questions, thank you, Kevin, for your presentation, and thank you, everyone, for joining. I'm going to turn off the recording.